So where we left off last class, and in the last video, if you're watching on the video, is with this definition of the logarithm. Okay, we had, if you look back up on the packet, or if you watched the end of the last video, we had graphed the function f of x equals 2x, the exponential function, and then we had manually created the inverse right here. And then we went and we analytically found the inverse. And what we realized when we got to this point where we swapped the x's and the y's is that we did not have a way to go any further. And so we came up with a definition. And the definition was of this thing called the logarithm. So the logarithm is a way to take an exponential statement and write it in another form. These two things mean the exact same thing. Okay, it's just a different way to express the same information. So the exponential statement here is x is equal to a to the y power. We're familiar with that. We've been working with exponents for like our entire math lives. And now that is equivalent to this statement, which is called a logarithm. So just to remind you real quick, a logarithm, the logarithmic statement is always equal to a power. Okay, that's the thing I always repeat to myself anytime I do a problem. This little number right here, or it's a letter in this case, is called the base. Okay, it's the same thing as what we call it over here in the exponential. It's called the base, and then equal to x. So before we begin new problems today, let's just gonna flip to page 2. You've got your definition in front of you. You were either here or you watched the video. That's my hope. And what we're gonna do is I'm gonna write down a little exponential statement, and you're going to, I'm gonna write down a little logarithmic statement, and you're going to write the exponential. So right here in this little white space that I have, I'm going to write that x is equal to log base 5 of y, and I would like you to please write what is the equivalent exponential statement. Just using that definition that is on your previous page, hopefully. Okay, so this is what we did at the top of this page. So we have gone through this. We've just applied the definition in some basic ways just to get used to manipulating it. And we're going to do a few more like that. So what is the base of this logarithmic statement right here? 5, excellent. What is the power of this logarithmic statement? X, the logarithm is always equal to the power, that's right. And then that's equal to the other thing, which is y. Okay, so those two statements are equivalent. It just depends on the situation we're in to which one we will use. And so what we're going to do now is we're going to solve some equations. Again, this is example 4. We're not used to thinking in terms of logarithms. So what I'm going to use is my definition in order to write this in a format that I can work with. So first step here, I've got my equation x is equal to log base 8 of 4. I don't know what that is, but we're going to figure it out together. So here goes. What is the base of this logarithm right here? 8, yes. What is the power of this logarithm? X. Logarithm is always equal to the power. So the power is always what's on the other side. So x. And what is that going to be equal to? What's the only thing left over? 4, perfect. All right, well, this is something we can deal with. We solved some equations like this at the end of the previous section. This is the only type of exponential statement I know how to solve, and we do that by equating the bases. So 8 and 4, I can write 8 and 4 both in terms of what base? 2, yes. Okay, so 8 is 2 to the 3rd power, and 4 is 2 to the 2nd power. We talked last time when we went through a whole bunch of these problems in class, and I'm hoping you're caught up with your homework and you've done some more on the homework. This is the power rule. I've got a power raised to another power. So what that is on the left is 2 to the 3x power. On the right, it's 2 to the 2nd power. And what I told you repeatedly last time was because the exponential statement is 1-to-1. If these two things, if they are equal, then what that implies is that the powers have to be equal. So I don't have to worry about the bases anymore. I can just think about the powers. And now it's just as simple as dividing by 3, and the value of x is equal to 2/3. So that's the solution. So we're getting two problems in one here. The first thing you're doing is we're practicing the definition, and then we're using some of the equation solving techniques that we already have. So what I would like you to do is right below this, exercise 7. So we're moving down to the next one. I would like you to use the definition and then go ahead and solve that, please. All right, so here's my logarithm. Again, this first part, this is just the definition. This is the new bit. What is the base of this logarithm right here? Yes, indeed, thank you. And what's the power? It's always equal to the logarithm's always equal to the power, so it's 4, and then that's equal to the only other thing, which is 16. So there is the equation we're going to solve. We're going to solve that by taking the 4th root of both sides. Back when we talked about using roots to solve an equation, I told you, like with a square root, if we have any sort of even index, we always get 2 answers. We get a positive and a negative. And when you put that into your calculator, the 4th root of 16 is 2. Now, there is one thing to mention we've got to be real careful of. When we talked about our logarithm and our exponential, the base, we are only considering what kind of bases in this class, in college algebra. Turn you back to the definition. Yes. Okay, the base is always going to be a positive number. So if you're asked to solve, like we are in this logarithm, for the base, I'm not going to think about the negative answer because we are only considering positive bases. So I throw that one out. And so my solution set is just going to be the set with 2 in it. That's it. Bless you. All right, try exercise 8. Exercise 8 is going to remind you of some properties of exponents. So we'll get to review that in case your memory is lagging behind. For the logarithm in exercise 8, what is the base? 4, great. What's the power? 3/2, excellent, thank you. And then that's equal to what's left over. Okay, so again, that's the new bit of information for this section, is the definition of a logarithm, the definition of changing between a logarithm and an exponential and vice versa. The rest of this, hopefully you remember, but if you don't, can anyone remind me, when I have a fraction in my exponent, what does the denominator of the fraction mean? The index of a radical, yes. So what this means, in case you had forgotten, is I have the square root of 4 to the third power. Your calculator can also tell you this, that you can put in 3/2 power or 1.5 and your calculator will be able to tell you, so that's fine too. So the square root of 4 is 2. And 2 to the third is 8, so that is my solution set, is going to be 8. One more of these problems where we're just using the definition of the logarithm to solve an equation. So go ahead and do exercise 9, please. All right, what's the base of this logarithm right here? Yeah, I heard you say it. Say it like you mean it. It's great. 2. And then what's the exponent? 3. Excellent. Again, we're just practicing in different situations the definition. The only other thing is this x plus 1. Well, this equation is a little easier than the other ones to manage. 2 to the third is 8. I'm going to subtract 1 from both sides, and that's going to tell me that x is 7. And there's my solution set. X is 7. So we're going to get more opportunity to practice the definition, but that is the most important part of this section, is getting used to this new way of thinking about exponents in terms of logarithms. Now, as you go through math, including this class, but if your math destiny is taking you to pre-calculus, etc., you're going to see 2 logarithms more often than any others, or what you're going to see is 2 bases are more frequently used than almost any others. So the first one is called the common logarithm. The common logarithm is just the logarithm base 10. Okay, since we are a base 10 number system, okay, the logarithm base 10 gets used a lot, and that's why it's called the common logarithm. Because it's used so frequently, kind of like the square root, we don't put the little 2 in the index of the square root. Because it's used so frequently, if you just see the words log without a base, it's base 10 implied. So on your calculator, you have you probably have a scientific calculator. You've got a log button. It says log. That's log base 10. Okay, so that is going to tell you the exponent when you have a base 10. The other most commonly used base in logarithms is a number that we don't know too much about, so I'm not going to focus on it too much in here. This is called the natural logarithm. It's log base this number e of x. E is an irrational number like pi. We're familiar with pi when we calculate the area and circumferences of circles. E is called the natural logarithm because it happens a lot in natural contexts, in nature. The way things grow or they decay in nature is usually with base e. E, if you look in your calculator, is approximately equal to 2.71828, and then it never ends, and so it keeps going. Just to give you a little bit of context, where does E come from? Well, that's something that you learn about in pre-calculus. Okay, you actually have to learn about something called limits before you can learn about where you can get this value of E. So all you need to know is that E is a number and it's a base. And when it's used, instead of writing log base E, what you'll see is ln. So on your calculator, you probably have an ln button, okay, and that is the natural logarithm. Okay, so those 2 are found on calculators. They're the most commonly used, and I just wanted you to be aware of that notation. Because we're not super familiar with E, when I use a logarithm, most of the time in here, I will be using the common log. And I just mention it because on your homework, there will be a few, but you don't have to memorize, I don't think, what the value of E is. I'm not worried about you memorizing it. Okay, so we're flipping the page. All right, we're going to end our section here with just some properties of logarithms, because what we're going to do, not today, but when we come back on, what's this, Wednesday? Monday, okay, when we finish up this unit, we just solved some logarithmic equations where we use the definition. Well, what happens if my logarithm is not in the form of a logarithm equal to a number? Am I able to solve those? And the answer is going to be yes. And we have some properties of logarithms that we're going to be able to use. So I just want to run through, and we're going to do some practice, some properties of logarithms. Remember, the logarithm is equal to a power. So these properties of logarithms, they kind of mimic some of the properties of powers, properties of exponents that we have. So let's go ahead and go. So this first one says, okay, what's the log base A of 1? Well, if you're ever in doubt, if you don't remember what the log base A of 1 is, what you can do is you can go over to your scrap work and go log base A of 1 is equal to some number X, I don't know. And now I can use the definition of the logarithm. The base of this statement is A. The power is X equal to 1. And probably at this point, you can tell me what power gives me a value of 1? 0. Yeah, so that's all. Remember, this logarithm statement is just communicating the exact same information. It's saying I have a base A. What power over here, because the logarithm is equal to a power, what power over here gives me 1? And you just told me 0. The next thing right here, the next two statements. These next two statements, they are based on the principle that the logarithm and the exponential are inverses. We talked a little bit about inverses in the first section of this chapter, and inverses kind of undo each other. When I take the cube root of something that's been cubed, I end up at the same place. Okay, so when I have the logarithm base A of A to some power, the logarithm and the exponent, because they have the same base, they cancel each other out, and all I'm left with is the value K. So if you want to write yourself a little note, because if you want to remember this later, I've mentioned that they're inverses, and you might just say something like, okay, they cancel each other out, and that's why I just end up with K. Same thing is true in the reverse order. If I have an exponential statement, and in that exponent, I have a logarithm. Those two things are doing opposite things. They're going in the reverse direction. So again, that the exponential base and the logarithmic base are the same, so they cancel each other out. So once again, you're just left with K. Okay, so that's just a little shortcut. If that comes up, you can take these properties to the bank. Okay, you don't have to explain it to me. You can know. Now, the more common ones you're going to see are over here on the right, the product quotient power rule. They're called the same thing as these rules for exponents. And so here's the product rule. Product rule says here this: if I have the log base A of a product, so X times Y, well, remind me, the logarithm is equal to a power. When I multiply my bases, what do I do with the powers? You add them. Great. So that's the same sort of thing. It's the same pattern for the product rule. I have the logarithm of a power. So what I'm going to do is I have the logarithm of a product. So what am I going to do with the powers? I am going to add them. So I'm going to take the logarithm of the first thing plus the logarithm of the second thing. Keep repeating to yourself, because this will help you remember the logarithm is equal to a power. So when I have a product, I add my powers, log base A of X plus log base A of Y. Same thing's true for the quotient rule. Okay, if I have the log base A of a quotient, so X divided by Y. Well, with my exponents, when I divide my bases, what do I do with my exponents? You subtract them. So the same thing is going to be true here. I'm going to take my first power, the log base A of X, and I'm going to subtract the second one, log base A of y. And finally, the power rule. If I have the log base A of x to some power, let's say n, just using the same letters that our book uses, there's nothing special or magical about the letters that I'm picking. Well, again, if I have a power raised to a power, what do I do with those exponents? You multiply them, yes. Just because I didn't get quite the response I was hoping for. If I have x to the fifth raised to the second power, I have a power raised to a power. Well, then you told me in the past, maybe you're just tired. I know it's Wednesday. You're looking forward to the weekend. We've got x to the 10th. You multiply. So the same thing is true here. And this is a nice power. This helps us simplify things. What that means is I'm going to take this power, the n, and I'm going to put it out front. I'm going to multiply the power times the logarithm, which is another power. And there we go. I get n times the log base A of x. So you can use those properties in both directions. When I'm solving equations, it's going to be handy when I start with these things that are unsimplified to go back to the left. Other times it's going to be handy, just depends on the situation, and we'll see a little bit of both. So example 5, I'm just going to run through. We're going to use the properties of logarithms. So these next 4 examples, their whole purpose is just practicing these properties because they're new and different. You haven't seen them before, most likely, and I've just thrown them out here. So we're going to take this and we're going to separate it into multiple logarithms. We're just going to use the properties. So the first thing I see is I've got a fraction. So I am going to separate this according to that fraction. So I'm going to take the numerator and the denominator, and I'm going to make separate logarithms out of them. So the first step is I've got the log base A of the numerator, which is x squared y. And then it's right on your page. I'm just accessing your short-term memory. What does the quotient rule say? What am I going to do with the, what operation am I going to do with these two powers? I'm going to subtract. Yes, so I'm going to put a subtraction here, and then I'm going to have the log base A of the denominator, z cubed. Perfect. I'm just going to do one thing at a time in each step. You're welcome to do more than one thing when you get better at this. I noticed that the first logarithm has a product, so I'm going to go ahead and I'm going to undo that. And so I'm going to take the logarithm of the first thing and the logarithm of the second thing, and I'm going to separate them. So I'm going to have the log base A of x squared. That's the first thing. And again, I'm just accessing short-term memory here. When I have a product, what do I do to separate these? You add, yes. So I'm going to have plus the log base A of y minus the log base A of the z cubed. There's no product there. There's nothing to do. Last thing, I've got exponents. So I'm going to use the power rule. So the power rule says this first term, I've got log base A of x squared. So what am I going to do with that 2 that's on the square? I'm going to multiply. I'm going to bring it out front. 2 log base A of x plus, there's no exponent on this middle term, so it's just going to stay log base A of y, and then minus, and then we've got log base A of z cubed. So I'm going to bring that 3 down, and I'm going to have 3 log base A of z. So again, it's just an exercise to help you remember these properties. So what I would like you to do is right below that is exercise 10. Exercise 10 is super similar to mine. My only word of caution is notice that there's 2 factors in the denominator. So be careful when you subtract. Make sure you distribute or you account for that. Okay, give it your best shot. We'll all learn together. All right, I'm going to get started. Check your work with mine. As always, please. I know this is hard stuff. I know it's new and different. If you've got a question, you don't understand why I did something, please feel free to ask me a question. Okay, that's why I'm here, and that makes me happy. Okay, so here we go. The first thing is I notice I've got this quotient, so I'm going to take care of that. So I've got the log base a of the numerator, which is x to the fourth, minus the log base a of the denominator, which is y squared z to the fifth. So far, so good. Anybody got a question, comment, concern? Okay. I'm not going to worry about the powers just yet. I always do the powers last when I'm going in this direction. So I'm just going to leave that log base a of x to the fourth alone for a moment, minus. Now, here's the thing that I meant earlier, and maybe my hint or my tip confused you, and I apologize. I'm going to now separate this, and I'm going to have two terms. This minus sign applies to everything that comes next. So you have to do one of two things here, just depending on how familiar you are with this. I'm just going to use a parenthesis. But when you separate it, if you're capable of doing this, it's going to be, I'm going to subtract the first term, and then I'm also going to subtract the second term. Okay, this minus sign applies to both. Okay, and the parentheses will help me do that. So I've got the log base a of y squared plus log base a of z to the fifth. Again, I'm not going to take care of the powers just yet. I'm doing one thing at a time because I don't want to conflate anything and do two things at once. You are welcome to combine steps. So I've got log base a of x to the fourth. Now I'm going to distribute this minus sign. And this is the part that I meant. If you could have done this all at once in your head, I totally get it. Okay, so then I have minus the log base a of y squared minus the log base a of z to the fifth. Which hopefully that makes some sense. Both of those terms were in the denominator. That's why you have the minus sign in front of both of those logarithms. Last step, I'm now going to do the power rule. And so I've got 4 log base a of x minus 2 log base a of y, and then minus 5 log base a of z. If there's a question, ask it. If there's not, I'm going to ask you to turn your attention to exercise 11. Now, exercise 11, what you're going to do first is you've got to rewrite that radical as a power. And we just saw in an example when we solved an equation, so hopefully that refreshed your memory. What do I do with the index of the radical when I make it an exponent? Where does the index of the radical go? Denominator. It goes in the denominator of the exponent. So the very first thing you're going to do is rewrite that as an exponential, and then you're going to use the properties of logarithms to rewrite that. Just going to be two steps, or maybe 3 steps. Okay, step number 1, got log base a of a, and then what I was alluding to, again, in case your memory is not fresh on exponents, the index of the radical becomes the denominator, so it's a to the 2/3 power. That's my exponent, 2/3. So then there's 2 things to do here. There's actually 2 properties of, or there's a property of logarithms, and then we're gonna figure something out here. I'm gonna bring the power down, so I'm gonna have 2/3 log base a of a. If you got to there and you stopped because you didn't realize you could go any further, that's totally fine. I get it. We're learning here at the same time. But notice this, I've got log base a of a. I'm going to come over here to the side because that looks a little funky. So I'm going to say log base a of a is equal to what? Maybe this is equal to something. So I'm going to use my definition of logarithms. I have a to the x power. So my base, my power is equal to a. So that means that power, that value of x has to be what? Yeah, this has to be equal to, when you have the base and what you're taking the log of, when they're the exact same thing, that's just equal to 1. And so then my final answer here is 2/3. So that was the purpose of that example for me. If you were wondering, maybe you got to the first step and you said, oh, that seemed a little too easy. I just wanted to make sure that I mentioned that when the base and what you're taking the log of are the same thing, that's equal to 1. All right, last problem of the properties, and then I've got one more little thing to mention, and then we're done with this, unless you have some sort of question, comment, or concern, which I would love to hear. So exercise 12, you're just going in the reverse direction now. In exercise 12, I've given you a logarithmic statement that's separated, and I want you to write this as a single logarithm. Little hint, I would do the power rule first. Okay, so I would do the power rule and then work your way down. Okay, so I did give you a little instruction. I would do the power rule first, get rid of those coefficients. In fact, you can't do anything else until the logarithms have nothing in front of them. So I've got the log base 3 of this x plus 2. And then according to the power rule, this next term is going to become log base 3 of what? X to the 4th. Fantastic. Thank you. And then minus log base 3 of just plain old 2. And then I'm just going to go left to right on the problem. Okay, these first two. Okay, these first two right here, I've got a plus between them. So that means I'm going to apply the product rule. It means when I write this as a single log, I am going to multiply these two things. So I've got the log base 3 of x to the 4th and in parentheses, x plus 2. Just going to leave it like that. And then minus log base 3 of 2. If you had the x plus 2 times the x to the 4th, that's fine. I just changed the order and put the binomial second. No big deal. And now the next pair has a minus sign between them. And the minus sign means that that's the quotient rule. So I'm going to now, when I combine these together as a single log, I'm going to make a division out of it. So now I've got the log base 3 of x. Oops, let me rewrite so that you can see what the... Let me be a little better of a writer here. Got the log base 3, and so the numerator is going to be x to the 4th times x plus 2, and then the denominator is going to be 2, and that is what we've got. Let me help you avoid a common mistake that students make, because I want you to get all the points you possibly can on the test. This 2 is part of what you're taking the logarithm of. So do not do this. Okay, so this is wrong. If you did not do this or wouldn't want to do this, don't write this down. But sometimes students, I don't know if it's getting lazy with the division bar or just misunderstanding, take the x to the 4th and the x plus 2 and then put the division bar under the whole thing, the 2. You don't put the division bar, you're not dividing the logarithm. The 2 is just dividing into the x to the 4th, x plus 2. Okay, so make sure your notation is clear right there. I don't want you to inadvertently mean the right thing, but write the wrong thing. Okay, one final thing from this section. This is getting kind of a little bit more, or a little gradually as time goes on, less and less useful because calculators are getting better. But my guess is probably 80 or 90% of you, if you have a scientific calculator, yours does not, you do not have a logarithm that does any base. Okay, so if you need to evaluate, for instance, example 6, if you need to evaluate the log base 5 of 17, meaning you want to know 5 to what power gives you 17, well, your calculator probably doesn't do that, but you can use your calculator to do it using the change of base rule. What the change of base rule says is if, again, all of this, I've got my positive values like we've said before. If I want to change my log base a of x into a new base like 10 or e so I can use my calculator, then this is how you do it. You're first going to pick your new base. I'm going to call that base b. That's why we have this letter, because you can change into anything. And so what you do is you say, okay, my numerator is going to be log of my new base of x, what I was taking the logarithm of before, divided by, now this whole thing is divided by, this isn't the quotient rule. I'm taking one log dividing by another log. It's a completely different thing. Log base b of the old base. So what that means is, let's say I want to use my calculator to evaluate log base 5 of 17. I don't have a calculator that does any log, so I'm going to use log base 10 because my calculator has that. So here's what I'm going to do. I'm going to say, okay, well, what that means is I can use the log base 10, which is just going to be the log of 17, divided by, and then the log base 10, or the log of the old base, which is 5. And now I can just go to my calculator, which I've got on my phone because I forgot to bring my other one. So I got to flip my phone to the side. And so what I'm going to take the log, my Apple calculator has log base 10 because they very much want you to know it's log base 10. So I'm going to take 17. I'm going to take the log base 10 of that, and that's 1.230. Don't hit anything. Then I'm going to divide by 5 log base 10 of that, and you get this. That it's approximately equal to, I'm just going to round to the 4th decimal place, 1.7604. If you have your calculator with you, please make sure you can get that value. If you can't, let's talk after class, okay? Make sure you know the steps. If you don't have your calculator, try it when you get home. And again, if you don't know if you're not getting 1.760, it's 6037444. But I've rounded. If you're not getting that, let's talk. I don't want you to miss anything because of that. All right, so do the same thing here. Figure out what the log base 9 of 100 is. You can use I'm going to use the common log base 10. If you want to use the natural log, it's fine. You will get the same exact value no matter what. Okay, so change base formula. I'm going to use the common log, but again, I'll just reiterate this. If you use the natural log, when you put your numbers in the calculator, it will be identical. Okay, it should not come out any different. So I'm going to use the common log, the log log of 100, what I was taking the logarithm of before, divided by the log of 9. And when I go to my calculator and I put in the log of 100 should be 2 because 10 to the 2nd power, but let's confirm. Yep, it is 2, then divided by the log base 10 of 9. And that turns out to be approximately equal to, I'm going to round to the fourth decimal place, 2.0959. And that is our introduction to this wacky thing called logarithms. You got any